well, yes, welcome everyone to GeoHug. So before we kick off today's session, I'd just like to take this time to acknowledge the traditional lands which we're all coming from today. I live on the beautiful lands of the Geological of the people of the Aurora Nation, and I'd like to pay my respects to the elders past, present, and future. So I'm thrilled to have Chris Kirkland joining us today. So Chris completed his undergraduate degree in geoscience at the University of St Andrews in Scotland and gained a PhD in isotope geology at the University College Dublin. At Curtin University, applying geochronology to reduce exploration risk and address geological questions related to the timing and rate of geological processes through deep time. So with all his experience, it is going to be amazing to hear from him today about geochronology on the grain to galactic scale. So it's going to be an awesome session. I hope you all enjoy it. Please use the chat. We'll open up the floor at the end. And yes, thank you so much for joining us, Chris. I really appreciate it.
No worries. It's a real pleasure to be here, and I'm looking forward to talking to you. Okay, so I've got the kind of lofty ambition of trying to go from the atomic scale to the grain scale, and hopefully by the end of the talk expand that all the way out to the galactic scale to tell us something about how the solar system and our solar system's voyage through the galaxy might have interacted with geology. So we're going across a wide range of different scales, and we're also going to go through a wide range of different times. And quite fittingly, this image in the background is a zircon grain. So that's everyone's favorite timekeeper as far as geologists go. And we'll briefly touch upon why zircon is such a favorite tool for geochronologists and why it's so important for understanding the deep time history of our planet. Okay, so what is geochronology typically used for? Well, it's typically used for telling us when things happen, so the timing. That's important because timing helps us understand how geological processes actually work. Are we looking at fast processes? Or are we looking at slow processes? The timing of a geological event connects us with what that actual physical process is. Now, for most geochronologists, this is how we analyze stuff. We look at our zircon grains. These have been polished to be half grain thickness, and then we're imaging them using cathode luminescence. And what this does is it really brings out the internal textures of the grains. So we can see these tree ring-like structures, and that allows us to interpret these parts of the grains as being formed during igneous crystallization. So if we date these parts of grains, we understand something about the timing of a magmatic process. But we can also see these dark regions. These are metamorphic overgrowths. So by using the shrimp, which we just heard about, we can analyze these small regions less than the width of the human hair, and we can get age information from these different domains. We can also get information from these CL bright domains, these low uranium domains, and they can tell us stuff like when fluids were interacting with our crystals. What's interesting here is this crystal is fractured. Fluids have entered the crystal and formed. So if we date here, we date the CL bright part, we're actually able to date the time of a brittle fracturing process or constrain the time of a brittle fracturing process. So that's the traditional way geochronology has been used. And Australia has really been at the forefront of doing this type of in situ geochronology, where we're using this petrographic information within the crystals to build up this detailed history of our planet and the processes that it has undergone. But geochronology also fits in with a wide range of different subject areas. And I like this kind of, this Venn diagram, if you like, and it shows geochronology as a tool that can be used across all these other sciences within earth science as a whole. So we can use it to understand metallogenic processes. We can use it to understand geophysics, tectonics. So geochronology is this really useful toolkit that can be applied to address a wide range of different questions. What I'd also like to do in this talk is, while understanding that geochronology tells us about the timing of events, geochronology and isotopes in particular, we can use to tell us about where material has come from. We can use it to track the source of material. Now that could be the source of sediments, and that's kind of provenance information, so we can understand how basins might have formed, the timing, but where the material has actually come from to fill a basin. But we can use that same provenance information and the same isotopic tools. We can use that to tell us about where manufactured goods have even come from, where artifacts have come from, like bits of pottery. So we can use these same tools to tell us a wide range of different things, from the very recent right through to our deep time archive of early processes happening on our planet. What we can also do is we can couple our timing information, so that's radiogenic isotopes. We can couple that to stable isotope geochemistry, and that allows us to track the sources of where material has come from and where fluids might have been generated. So what I want to do is give a very brief introduction into how these tools work, to give you a little bit more context about what I mean about a radiogenic isotope and what I mean about a stable isotope and how that works. Okay, so this is my naughty 101 geochronology diagram. And if you get a handle of this, hopefully it'll set you up well for how we're going to use these tools to tell us about the history of our planet. So on the left-hand side, we've got an example of a rock, and our rock contains some parent isotope and some daughter isotope. And through time, more daughter will be produced. So if we understand the rate of change between the two of these, we might be able to say something about the age of this rock. But there's a key thing here. There was always some daughter present in this rock, and that creates a bit of a problem, right? Because our scheme of parent changing to daughter, if there's already some daughter there, our relationship between the two, which changes over time, will be a bit messed up. So we need some mechanism of extracting or taking away the daughter product so we have a clock. And one way that we can kind of do that is look at minerals that only contain the parent isotope. And a good example of that is zircon, and that's why we like zircon, because zircon loves uranium. Because zircon has so much uranium, over time it will produce lead, but there'll be no lead in the crystal to start with. So through time, we'll start to produce our daughter product, and that daughter product will increase. So we've now got a really cool clock. We've got a clock within this crystal that tells us how old it is. But we can also use stable isotopes. Now, stable isotopes are things like lead isotopes in feldspar. So lead in feldspar is kind of interesting because our K feldspar grain doesn't like uranium. So it's not going to incorporate any uranium. So it's not going to change its isotopic signature, its lead isotopic signature through time. So that signature of our daughter lead isotope, we can use to relate back to the rock. So we've got a clock in our zircon uranium lead system. That's great. Our K feldspar, our lead isotope system in our K feldspar, we don't have a clock, sad clock face. But what we do have is we've got this source signature. We can link the daughter because it's not going to change through time. So we can use isotopes in two different ways, a clock or as a source tracking tool. So I like to think about geochronology as having a scale. So a scale ranging between a geochronometer, something like zircon, uranium, lead, but then at the opposite end, with other sorts of isotope schemes, as we've just talked about, we can use isotopes as a source tracking tool. So an example here might be the mineral apatite. Apatite loves strontium, but it hates rubidium. So the isotopic signature of strontium within our crystals is going to tell us something about the fluid our apatite grew from. Then we have systems that are kind of intermediate between the two. So something like biotite, rubidium, strontium, it's a clock, but it also gives us source fluid information at the same time. And garnet SMND, you might have heard of that. That also is a geochronometer telling us about the age of things, but it also allows us to track the fluid that our garnet grew from. We've got another scale in geochronology as well, and that's the scale between a thermochronometer and a geochronometer. So a geochronometer tells us about when a crystal grew. A thermochronometer tells us about a time temperature point. It tells us about the time a crystal passed through a specific temperature, and that's really handy. So this naughty diagram in the center here tries to explain that closure temperature idea and this time through a specific point. So our yellow crystal at the top here, is at high temperature, above the closure temperature. And that means our parent isotope will produce daughter isotopes, but those daughter isotopes escape from the crystal, so we don't have a clock. On cooling, so our crystal cools, and it'll reach a temperature point that there'll be no diffusion of daughter product. So that means our clock will start. So over a wide range of different temperatures, we've got a range of different minerals and a range of different isotope schemes that mean we can actually track a parcel of rock through the crust as it moves and changes through different crustal levels and different temperatures. So we can build up this detailed picture of both when material forms, but also how that material has moved through the crust. So for example, our biotite rubidium strontium system normally tells us about when biotite has transited through about 400 degrees C. Our apatite system, apatite uranium, thorium, helium, is a low temperature system, and that tells us when our apatite was passing through about 90 degrees. The other side, zircon, uranium, lead, that tells us about crystallization in a magma. That is actually probably when the crystal grew, because it closes to diffusion of lead, diffusion of the daughter, at about 900 degrees C. So already we can see that we can use isotopes and geochronology to tell us lots of different things. We can use it to track where material has come from. We can use it to track fluid rock interaction. We can use it to track when minerals grow, but we can also use it to track the thermal pathway of blocks of crust. So how do we do this in the lab today? Well, kind of in Australia and at Curtin in particular, we've kind of pioneered the idea of analyzing material in thin sections, so polished pieces of rock that maintain their petrographic context of the mineral we're interested in. So we scan these thin sections and we typically color code them with mineralogical identification. So for example, in this rock slice, I'm interested in apatite, which is the green mineral. So I can find my green minerals in this and I can go and analyze them with a beam-based technique. So we usually would fire a laser beam at our grains, and we would then extract that material into a mass spectrometer that tells us about the parent to daughter ratio. It tells us about our isotopes, and we can pick which style of instrument we want to use depending on the spatial resolution we want. Do we want to analyze very small grains? We would probably use the shrimp. That fires an ion beam. It's about 20 microns across by about 1 micron in depth, and it's about 15 minutes to 20 minutes on analysis. Alternatively, we can use a laser ablation approach where we fire a laser beam, which is about again, could be a 20 micron laser spot, but it goes down much deeper. It goes down about 20 to 30 microns in depth. And that ablated material goes into our mass spectrometer, and it gets, again, separated on a mass to charge ratio, and we can understand our parent to daughter ratios. So this is the kind of approach we tend to use. What I thought would be nice is to kind of go around and look at geochronology at different parts of the rock cycle and try then at the end to end up saying something about the driving forces that might have influenced geology on our planet at a much bigger scale. So let's look very briefly at how we can say something about a magma and where a magma might have come from and why that's important in our mineral systems concept to understand where it might be fertile to go to look for different mineral systems. So the way, this is a photograph of our lab. We've got our laser ablation system here in the center, and you can see all this pipe work. This gas that comes out of our laser ablation system, we pipe it in 2 different directions. We send one to a quadrupole mass spectrometer that measures the uranium and lead isotopes. So this gives us our age. And at the same time, so out of the same volume of ablated material, we can also split the gas into this multi-collector ICP-MS. This ICP-MS will measure a source signature. So we're getting age and source information. And I'll go into a little bit more detail about what that source information can tell us. The gas, by the way, that passes from the laser, it's in an aerosol, and it'll go into this kind of torch blocks. This is an ICP-MS component here, and this is basically a plasma, a bit like the sun. So we pass an aerosol into the sun and it ionizes it, and then it can pass through the rest of the instrument. So we're taking physical material, we're turning it into an aerosol, turning it into electrons, and we're measuring electrons on glorified multimeters. And then we're making ratios of multimeter voltages to calculate ages. Picture some lovely zircon grains example, and my spot, my highlighter spot here is actually similar to the size of a laser spot on these, so we could get multiple laser spots to say something about the different age domains within these crystals. Okay, so a little bit more isotope geology, just for a little bit of context. And if you get your head around this, it'll mean when I present some data, it'll make a lot of sense. So what I want you to notice on this diagram is we've got an isotopic ratio on the left-hand side that has a daughter at the top. So this 176 hafnium is a daughter product, and it's produced from lutetium. And we've got time on this axis. So younger this way, older this way. So we start off with chondrite. Now, chondrite is just basically how we think the Earth started out like. So chondrite contains some lutetium. So some lutetium over time will produce some hafnium. So we'll journey upwards on this diagram as we're producing more of the radioactive or radiogenic product. But lots of processes in the Earth are fractionation processes, so melting processes. So we melt something, it fractionates. So we have a residual material that gets left behind. We have material that separates away. The lutetium-hafnium system fractionates so that lutetium stays behind. It likes to stay in the solid, so it'll stay behind in the mantle. So if we have more lutetium, we're going to have more of the daughter product. We're going to get more 176. So we go on a steeper trajectory. If we've got some crust, crust likes hafnium, doesn't like lutetium, so it's going to go on a shallower trajectory. So we've got a crustal melt here and a mantle melt. They're going on different trajectories. Now, the cool thing about zircon is we can date it. That's awesome. We can date it using uranium lead, but zircon likes hafnium as well, and it hates lutetium. So that's the idea of this kind of source signature being trapped within our zircon crystal. So I can go to the lab today, and what I measure in the lab today is going to be very similar to what it was in the past, because there's so little lutetium in this, but it has got hafnium that I can measure. So that hafnium signal is really like a surname. So my surname is Kirkland, kind of tells you I came from Ireland or Scotland. The zircon's surname, if you like, is its hafnium isotopic signature. It tells us, has this zircon come from a fluid that came from the mantle, or has it come from a fluid that came from the crust? With that in mind, we can go all over the planet and look at our zircon grains and date them, but also get their isotopic signatures. So we've done that for a lot of Western Australia. And I'd like to give just an example of the Albany-Fraser origin because it's relevant for mineral systems. And it tells quite a cool story about the development of this margin of this old gold-bearing province, this Yilgarn Craton. So traditionally, the Albany-Fraser origin was thought to be this Proterozoic mobile belt that was accreted onto the margin of the craton. But our hafnium data actually tell us a different story. So this is the location of our samples on a map. This is the Albany-Fraser origin here, and we're getting out into the Euclid Basin here. This is the Archean Craton itself on this side. So what we can see on this diagram, it's an evolution diagram. So we've got time on this axis, and we've got hafnium isotopes on this axis. Upwards on this diagram, remember, means more mantle. Downwards on this diagram means more crustal material. So what we can see is that through time, there seems to be periodic episodes of more mantle addition. But those periods of mantle addition also reworked older crust. And we can isotopically connect this older crust all the way through to bits of the Yilgarn Craton. So what's happening is this is all rooted on the Yilgarn Craton, and we're pumping it full of new mantle additions. And we're periodically adding mantle material. And we can see this extension probably started to commence at about 2 billion years ago. So at 2 billion years ago, we had addition of, as an isotope geologist, I'd say juvenile. I just mean mantle material was being added into this older crustal component of the Yilgarn Craton. And that's deviating our values upwards to more positive values. And then what's happening is we're reworking and remelting that crust. So we're going along this kind of direction and then having periodic additions of new mantle again. What's interesting is these periodic additions of new mantle tend to correlate with metallogenic episodes when we're having metals move in the crust. Another pointer, see this weird symbol here, this is epsilon hafnium, and that's just because geochemists or isotope geologists are kind of lazy-assed. It basically means we don't have to deal with really small numbers here. So it's parts per 10,000 deviation from this black line, this chondritic reference frame. So it just means things are easier. It's a normalization scheme. So this is essentially time-resolved geophysics. Geophysics is an image of the crust today with all those other processes added together. So we got this kind of combined image in geophysics. But with isotope geology, and if we look at isotope geology over space and time, we're getting this kind of time-resolved map where the breaks and gradients in that map might tell us where major structural boundaries are between different pieces of crust. So we can take this information and we can then show it spatially. We can show it on a map. So we can actually see here, this is the evolution of the Yilgarn craton through the, from about 2 billion years ago. So we see the development on the margin of the craton of new juvenile material. That juvenile material has got these more positive values, whereas older crust on the ancient part of the craton have got these strongly negative values. As I kind of said before, the reason this is useful from a mineral systems perspective is we know that there is a good correlation between new mantle input and gold occurrence, but there's also a relationship with other metal systems as well. If we look at the craton margin itself, where the Fraser zone is, so the Fraser zone's got lots of gabbros, and it has obviously the Nova nickel copper deposit. If we look at older granites within that region, so these are 1.7 billion year old granites in that region. So that's older than the Fraser zone itself and older than the Nova deposit. The deposit is 1.3 billion years old. So older than the deposit, there already appears to be a zone of new mantle addition, preconditioning that part of the origin to new mantle input. So you can start to think about the older structure of the craton and its interaction with the margin has had some influence in where later systems, mineral systems are forming. Okay, let's moving on. That's kind of an introduction into source tracking in a magma. Let's go and look at some metamorphic processes and fluid rock interaction that has implications for, again, gold systems. I'm going to stick with an example from Western Australia and the Albany-Fraser origin. And I'm going to talk about this zone called the Tropicana zone. So the Tropicana zone is a reworked old Archean sliver on the margin of the Yilgarn craton. And obviously that has the Tropicana gold deposit. So kind of an interesting question is, when did gold mineralization occur there? And there's been some work that points to early sanucatoid magmatism. So sanucatoid magmatism, it's a type of magmatism that is fertile for gold. It reflects an enriched signature, probably again from the mantle, and high magnesium granites. But we have an early metamorphic event that formed granulite facies metamorphism, and we have an early gold event. But the Albany-Fraser origin on this time-space diagram, we can see that there's multiple overprinting events and multiple other magmatic and metamorphic events. Two of the big events are stage 1 and stage 2. That happened at 1.3 billion years ago and 1.2 billion years ago. And they overprinted these much older rocks. These 2.7 billion year old rocks got overprinted. Did these later overprinting events have any effect on the gold bearing systems? With some new technology, we're actually able to address that, and we can do it in a kind of a neat way. So rather than using uranium and lead, which helps us date zircon, we can use rubidium and strontium. And why that is cool is that allows us to date much more framework minerals. So our zircon grains are accessory minerals, so they don't form a large proportion of our rock. But by using rubidium strontium, we can date things like biotite, which are the main fabric forming mineral and may actually be associated with gold. So we can directly date things associated with larger scale structures, but also directly associated with the mineralization we're interested in. So why can we only do this now? So rubidium strontium has been around for quite a long time. I remember when I was doing my PhD, we used to do it. It used to take months and months and months. We used to have to do column chemistry and go into a clean lab, get suited up, go and put things through a column and hopefully not forget where you were at and waste a month's worth of work. Now we can do all that work in literally a day by firing a laser beam and letting the machine do all that horrible, difficult chemical separation work within the instrument itself. So why can we only do it now? Well, we're interested in the rubidium-strontium isotopic ratio. The problem is the strontium ratio that we're interested in is two isotopes that are not very abundant. So 86 and 87 strontium are actually way less than 10% of the mass of strontium that's present. So we need a very sensitive instrument. That's the first thing. But the second thing is that rubidium, the parent, you can see it's 87. It's 87 rubidium, but it interferes with 87 strontium. It's in the same place. It's got the same isotopic mass. So if I go to my mass spectrometer and want to measure 87 strontium, I'm going to end up measuring rubidium as well. So there's two ways around that, either long, laborious chemical separation. No thanks, that takes too long for me. Or I can do the chemical separation using my mass spectrometer. My mass spectrometer that we need is a triple quad instrument, and these are kind of brand new. They work by having two quadrupoles and a reaction cell in the center. And I'll talk a little bit about how that works in the next slide. So the quadrupole, very cool the way it works, is the quadrupole causes this rotational movement of the isotope of interest. And where there's good coupling, the isotope we're interested in will pass all the way through the quadrupoles. Great, and get to our detector. That's cool. But those species that we're not interested in will collide out and not make it through. So we have a quadrupole at the start of the instrument doing some separation, and we have a quadrupole at the end of the instrument doing even more separation. So we've got two quadrupoles, but we also have a reactive gas in between, and that's the new part really. So we pump this cell full of fluoromethane, and that fluoromethane will react with the elements and isotopes and atoms and collide out species that we're not interested in. And that means, well, we get this happy little isotope of strontium at the end that we can actually measure. If we didn't have all this separation kit, what happens is we get all the isotopes piled up on top of each other and we can't measure our ratio. So why do we want to measure rubidium and strontium? Last one of these complicated diagrams, sorry. This is called an isochron diagram, and it's very cool. So the way it works is if we've got different amounts of parent, so we've got a small amount of parent here and a large amount of parent at this end, over time, they're going to produce different amounts of daughter. So at this end, where we've got lots of parent, lots of rubidium, we're going to produce lots of strontium, so we're going to migrate further. Rather, at this end, at the green end, we've got very little parent, so over time, we're going to produce relatively less of our radiogenic strontium. The cool thing about this, of course, is that through time, this is going to tilt, okay? So at 10 million years, it's going to give us a slope of something like that. 20 million years, a steeper slope, 30 million years. So as time goes on, the slope is going to get steeper. And that's important because what that means is the slope is proportional to age. So we can use the slope of these sorts of diagrams to tell us about the timing that biotite went through its closure temperature. So when it started to accumulate its daughter product. We can also do another interesting thing. You'll notice that through time, this slope will rotate about a single point, this point here, and that's our initial ratio. And that's useful because that tells us about the composition of the fluid that our biotite grew from. Also, things like apatite, if our apatite grew along with biotite, because apatite doesn't like rubidium, but loves strontium, it's just going to plot down there the whole time. And that pins this bottom part of the diagram. So our apatite is never going to move, but our biotite is going to move. So we have information about source, and we've got also information about age. Pretty cool. That's just an example of what I was trying to animate, if you like, with my laser pointer about how through time the slope changes. So let's look at biotite in Tropicana. Well, there's two different types of biotite. We've got this kind of nice coarse biotite. You can see it here. And it's earlier. And then we have this later biotite that's finer grained and intergrown with quartz. So these two different generations of biotite, and that would not be possible to separate out and analyze using column chemistry and a thermal ionization mass spectrometer, but we can fire a laser beam here, and we can fire a laser beam here and see if we get the same age. So two different mineral assemblages, two different biotite generations. Both biotite generations are associated with gold, and the older biotite generation also appears to be associated with apatite. Okay, so what do we get? Well, kind of interestingly, our older biotite generation in red here goes through where apatite plots, and we get an age of 25, 30 million years. And that's consistent with other data that's pointed to this old gold generation in the Tropicana zone. But note that our other generation of biotite, it's finer grained, so it's harder to analyze, but we can get an indication of a younger age for that finer biotite better on this sample. We can see it quite well here. We've actually managed to date this 1.2 billion year old later biotite, also associated with gold. These are just backscatter images of what those different generations of biotite look like. These are our laser spots. You can see the molten biotite where we've ablated it out. And you can see texturally there's a difference between our early biotite, nice and clean, and our later biotite where it's associated with these titanite X solutions. So this careful petrology allows us to link these different generations of biotite to different gold generation events. And piecing that together, well, okay, so we've got an early gold generation event, but we have a later remobilization of gold associated with stage 2 of the Albany-Fraser orogeny, which makes sense because this is a widespread event throughout all this margin, and it was associated with mineral overgrowth. And that's kind of useful to know because it's a widespread fluid event all along the origin at that time. So we've demonstrated that at least some of it is associated with remobilization of gold. Simple model for what people have suggested, the Tropicana zones, a rifted piece of the Yilgarn craton that's been recompressed and thrust up onto and back onto the Yilgarn margin. Later events through here have mobilized fluids along these shear zones and have remobilized the gold. Okay, moving on quickly, we can look at sediment as well. So we can use geochronology to help us understand where sediment has come from, how basins might have formed. So a day at the beach, you know, we can see these dark, heavy mineral bands, lots of ilmenite, zircon, rutile, titanite in our sand. We might be interested in our zircon grains because zircon is very robust, and it can tell us about the deep time history of where this sediment might have come from. We could also look at other minerals within our sand. We might be interested in more first cycle material that hasn't been reworked as much. We could look at apatite or titanite then. But zircon is very robust and it kind of survives multiple cycles of erosion and reworking. So we're going to look at that. So part of the complexity is our sand on our beach, if you like. Has it come directly from a granite source into our basin, or has it been multiply reworked? In other words, has it come from one granite source into a beach sand? Has it gone from that basin into another basin into a sedimentary rock? being reworked out of a sedimentary rock, being reprocessed multiple times. So how can we try and get this idea of this full life cycle history of our grain to understand where it's come from? And the reason we've kind of been interested in this work is to better understand heavy mineral sands deposits. Just as a case study, let's go to the down south coast of WA, really nice area, lots of nice wineries, lots of nice beaches. And we took a sample from a beach down here. Remembering the paleogeography of Australia, you know, we were connected to Antarctica. We have the old Yilgarn Craton. It's surrounded by the Albany-Fraser origin, this Proterozoic origin that extends into Antarctica as the Wilkes origin. And then up the western margin, we have this Kunga origin that stretched all the way to Greater India. So we got lots of source regions that could have supplied zircon into our beach sand. How do we find out which origin, if you like, supplied zircon? The easiest way to do it is to kind of look at these fingerprint diagrams. So these are the age of zircon grains. So our beach sand is right up here at the top. Okay, so this is a modern beach sand. You can see it's sitting, this beach is sitting right on top of the Yilgarn Craton, right beside the Albany-Fraser origin. And you can see there is very little Yilgarn Craton or Albany-Fraser detritus within this modern beach sand. Most of the heavy mineral grains within this beach sand are coming from the Kunga origin. The Kunga origin is quite distant from the beach at the minute. So we can see this Kunga origin signal matches quite nicely with what's in Antarctica, but we can see the same signal in other sands and other basin deposits across Western Australia. Let's try and get a little bit more information on where this sand has come from. What we can do is we can look at our uranium, thorium, helium system in the same zircon crystals. So rather than their age of growth, what we're looking at now is their time through about 200 degrees C. So we're looking at the thermochronology information, the time through a temperature interval. And this is a fingerprint, if you like, of that age for that passage through 200 degrees. And you can see most of the zircon grains passed through 200 degrees at about 450 million years ago. That is very similar to uplift within Antarctica, indicated here in the black, dark black, but not very similar to other regions within either Western Australia or elsewhere in Australia. So it doesn't match grains elsewhere in Australia, but it does strongly match Antarctica. So that's kind of interesting. If you're on a beach in Western Australia, there's quite a proportion of the material you're lying on has probably come from underneath the inland ice in Antarctica. What do the grains look like? Wow, they're nice magmatic grains with these beautiful magmatic textures, but you can see they're quite rounded. So these grains have been far transported in fluvial systems. So there's been various models proposed for these fluvial systems, and one is this kind of transcontinental river system that flowed from Antarctica all the way over Western Australia and deposited stuff within the Canning Basin out the top of Western Australia. And that's been suggested as a kind of an express route, if you like, a single river system turning into a big braid plain that transported material very rapidly from Antarctica all the way north. I think the work that we've done on the modern beach sediment here would suggest a slightly different process, because we've picked up small evidences elsewhere of little small basements, little small regolith components that also have this signature. So what we would say is that material did get transported from Antarctica, but it got moved and started to get recycled in a cover sequence on top of the Yilgarn Craton, and got multiply reworked back and forward, back and forward, back and forward, before eventually some of it making its way north. But it's a multi-cycle process. So it's not just a fast braid system taking stuff out. We say there's probably a more recycling-based system. So by using multiple different chronometers, we're able to point to an Antarctica signal. having grains from Antarctica is actually really useful because we're not actually able to sample that material in Antarctica, right? We can't get beneath the inland ice. So having these grains tell us something about the geology of Antarctica. So we can look at their hafnium isotopic signature, and that tells us maybe about how Antarctica got put together. So we've got this idea of this full life cycle of zircon. You know, when the parents meet, that's very much like lutetium hafnium telling us about when the source material was formed. The birth of the crystal, we can tell that using uranium-lead zircon. That's what we've talked a lot about today. But we can also tell uplift processes using uranium, thorium, helium. And in the old age, in the detrital sand, well, that's a really good sample media because we can tell this full life history of zircon grains. That's basically where I wanted to get to with, you know, individual case studies. I wanted to maybe finish with a bit more of a provocative overview very quickly to talk about, you know, the driving forces that maybe are responsible for at least some of the Archean geology we see in Western Australia, at least. So what I wanted to talk about is about the periodicity of events and using geochronology to understand what are the larger scale drivers. So, you know, if we have a geological process, let's say this is magmatism, there may be an anomalous magmatic event once every 10 million years, 20 million years, 100 million years. But if we change our length of time that we view something, we might find that that anomalous event is actually periodic. It happens on a set frequency. And there's lots of things that seem to have a set frequency in geology. Probably one of the best evidences of that is this supercontinental cycle, this periodic breakup and aggregation of supercontinents. And we kind of know that kind of fits into metallogenic epochs. When we've got periods of more rifting, we might find more specific ore deposit types where we're getting more collisional origins. We might tend to find more orogenic gold, for example. We also have cycles on a whole different range of scales, of temporal scales. So we even have solar cycles, right, on a much faster frequency. We have cycles that may tell us, we see cycles within sedimentary basins as well. So there's lots of different frequencies of periodic events in geology, and understanding those periodic events maybe can help us understand what's actually driving these processes. So since about 1950, there's been this idea of 250 million year pulse in our planet, the rhythm of our planet, where mountain building events seem to periodically occur. Basins seem to occur on the same sort of frequency, and climate, obviously. So we, you know, arguably these things feed back into each other. So as maybe mountains were built, you know, we'd have those mountains influencing climate. And I mentioned this already, that there seems to be some relationship to mineral, temporal mineral systems happening at specific periods of time as well. So how do we actually do this sort of analysis? Well, we've been talking a lot about things through time, you know, this kind of noisy signal through time. We can break this into its frequency components. So the periodic signals within this process, we can mathematically extract out. And the way we do that is pretty much like taking a cake. I like Dundee cakes. I like Dundee cakes mainly because they got quite a bit of whiskey in them. But we can take a Dundee cake and we can unmix it. So we can unmix our Dundee cake and find out it's got some orange in it, some sultanas, and some whiskey and butter and eggs. We can pretty much do the same thing with our temporal record. We can unmix our temporal record into the frequency components. And we do this using Fourier transform. This is probably mathematically one of the most significant steps forward in science and engineering that's maybe ever been made, because it allows us to understand the driving frequencies within any signal. So this guy, Joseph Fourier, was a very interesting dude. He was a proponent of the French Revolution and was also in the French military. But he kind of viewed everything through circular processes. So he basically was able to describe a frequency of an event through these three components. So the rotation speed of a circle, the size of the circle, and the starting angle of the circle. I'll try and explain that better with these animations, because it's actually, well, mathematically it's quite complex. conceptually, if you get it, it's quite easy. So let's start with this yellow sinusoidal curve. So you can see this nicely goes up and down. We can describe that with our circle, just our simple rotational circle, going round and round. Notice this much more complicated signal here in green. We can break it into its frequency components. So we've now got two circles. We've got this big circle describing the longer term period, but then this smaller circle describing the higher frequency component. We can continue with the blue waveform, which is even more complex. So we simply add another circle on to make up the next frequency component. And then we can do the same again with this red circle, getting to a much more complicated pattern. So what this allows us to do is pick out the individual frequency components. So let's do that for our hafnium isotopic data through time. So this is Zircon hafnium isotopic data, thousands and thousands of data points. We have age information. We've got hafnium isotopes. Remember, upwards on this diagram is more mantle, downwards on this diagram is more crustal reworking. So we can see through time, you know, there's periods when there's more mantle being added. There's periods of time when there's more crustal reworking, and there's some sort of oscillating frequency through this. So let's go and play this in two different places. Let's go and play this game in the North Atlantic craton. That's been regarded as a good study area for early Earth subduction processes. And let's go to the Pilbara craton in Western Australia, which is regarded as the archetypal example of vertical tectonics. So not horizontal processes, not subduction, but a sagduction style. So two kind of different tectonic regimes on the early Earth. What we do is we do our Fourier transform, and this is the output from our Fourier transform. So this is the frequency. This is when events are periodically happening, and this is how strong that signal is. The red line is background noise, and the green line is 95% confidence. So you can see in both the North Atlantic craton and the Pilbara craton, we have a signal that's above background noise and close to or above the 95% confidence in a 200 million year frequency. Lunar spherules, so these are glass beads from lunar return missions, and they've been dated. Note, they also seem to have this 200 million year frequency. So what's going on? What do we know has a 200 million year frequency on our planet? Okay, this is where we go really big scale, but just stay with me. Roughly every 200 million years, our solar system has transited between the galactic arms of the Milky Way. So the Milky Way is a barred spiral arm galaxy. So it has four arms, or it's envisaged to have four arms around this central bar. The rotational direction of our solar system is it like this, and our spiral arms of our galaxy will also rotate. They both are rotating, but our solar system is moving faster than the galactic arms. So our solar system is kind of surfing in front of and then into the next galactic arm. And the passage between arms matches extremely well with our Fourier transform data. The best way I can kind of describe this is if you envisage, these are star systems. The star systems are migrating. They're coming into these density waves, which are the galactic arms, and they're slowing down. It's kind of like a traffic jam. So imagine cars driving up to a set of traffic lights, slowing down, and then speeding up away. And that's how solar systems transit through the galaxy, through the Milky Way. It's quite well established in astrophysics. Basically, we have our stars migrating around. They slow down in these gravity waves, and then they speed up away from the gravity waves again. So everything is rotating, the arms are rotating, but the stars are migrating faster than the arms until they pile up in our traffic jam. So how could this periodic transit through the galactic arms have any effect on Earth and the inner planetary bodies? So it appears to affect our moon as well. The easiest way to do that is periodic cometary impact. So probably what's happening, or one proposal, is that the Oort cloud, this distant cloud of icy planetesimal material that never fully accreted into the rocky planets, may be periodically disturbed and thrown inwards into Earth crossing trajectories. So this material, this cometary material, could be periodically disturbed every 200 million years, causing impacts on Earth. And that's why we're seeing that frequency in our crust production history of early Earth, of Archean Earth. People will point out that most impacts on Earth are from near-Earth objects from the asteroid belt. The thing with that is that that's a much more chaotic process. And that's because it's material that's closely bound to the gravitational field of the sun. Oort cloud material is much further out and is much more easy to disturb with this transient passing through the galactic arms. Importantly, Oort cloud material, the average comet that comes from here, is 3 times larger than the typical asteroid. And moreover, it will be coming at a much higher speed. So the amount of energy that will be imparted into our planet from a comet is going to be orders of magnitude or near orders of magnitude larger than near-Earth material coming in. So the reason why we might see a periodic signal is simply because these events are big events. Can we do anything else to pick out this frequency a bit more? I think we can. Here we're looking at zircon oxygen isotopes against time. Oxygen isotopes tell us where melting happens. Upwards on this diagram is more reworking of crust at depth. Downwards on this diagram beneath the mantle field is shallow melting. The periodic entry and exits of our spiral arms are in pink. And what we can see is that there are these excursions in our zircon data from the Pilbara Craton early, and they kind of match our entry and our exits of the spiral arms. Also, direct evidence of impacting spherical beds occurs at the start of each of these galactic arm crossings. I think this is quite profound, and is maybe telling us about a major driving process. Much like plate tectonics is our driving process for much of the more recent Earth, the early Earth, I think quite a lot of the drivers might have been coming from these large-scale impact processes. It's just to point out that the periodicities and the timings we see of these events tend to match the galactic model quite well. Okay, so why at the start and the end of these galactic arm crossings? At the end is probably because just it's statistical chance. We've got more period of time within an arm, so we've got more gravitational processes that have affected our Oort cloud. And at the entrance of the spiral arms, well, that's where we find giant molecular clouds. And I think this is one of the most spectacular images. It's from the Hubble Space Telescope. So we obviously can't take images of our own galaxy very well because we'd be looking through it, but we can look at other galaxies and see how they function. So this is a spiral arm of another galaxy, Ursa Major. And we have here these giant molecular clouds. So these giant molecular clouds are where stars start to form. So these bright areas are just after the galactic arm. So a solar system, just like our own, transiting through one of these arms is clearly going to have seen very different gravitational effects through time. So if we believe the astronomical models for the spacing of our spiral arms of our galaxy, I would argue that we can see an effect on that on our early planet. The effect being impacts causing deep decompression melting, but also causing shallow melting and creating these buoyant seeds, which crust can nucleate on. And that's probably what we're tracking in our hafnium isotope system. All right, so I've tried to give you a whirlwind tour of geochronology from the grain scale all the way through to the galactic scale. I've talked about a wide range of different isotope schemes, how we can use them for dating, but also how we can use them for source tracking, shown how stable isotopes are useful as well as radiogenic isotopes. That's basically where I'd like to leave it. If you're interested in the sort of research we do, please follow us on Twitter, check us out on Google, and we have some free software, but also lots of both talks and some of our research papers online, and they're accessible for free. So check us out, please.
Thank you so much, Chris. That was awesome.
No
I really appreciate that.